Hey guys, so it turns out that Godot does have Slerp implemented, which is not a huge surprise to me. It's obviously a very valuable function, and it's in the Vector3 class, which I honestly just didn't think to look at. You look at Lerp, it's actually a variant. But you know what? There's still a lot to be said for having implemented and understood it ourselves. So why don't we go one step further and introduce the Flerp, that's F-L-E-R-P. I quasi-invented the name. It may have been used before me, though. That is functional linear interpolation. If you look at the game now, I went ahead and added some transparency to the globe so you can see points where it might be traveling beneath it. Well, we've got our satellite over here, and if I click somewhere, it flies up above the surface and then comes back down smoothly right on top of the globe. So how did we end up doing that with Slerp, right? Well, more like we ended up taking inspiration from Slerp and writing our own function for it. Let's look at Flerp. I don't know why that's there. So, for Flerp, we take P0 and P1, just like before, our start and end points. After that, we take an additional value that is a callable, which is like a function. Anything that has first-class functions, you want to use a first-class function here. Followed by a field for our distance along that fraction between the two, and a value to normalize by. One thing I want to drive home is this divided by sine of omega. That's not exclusive to spherical linear interpolation. You always want to make sure that you've normalized the value, or you're going to get some odd results. What does it do here? It calls f for 1.0 minus t and the normalization factor, multiplies that by p naught, then adds the same function called on t and the normalization factor times p1. Very similar, right? So in theory, if we had the right function, we could do a spherical interpolation. And that's actually something I've added up here. Let's go ahead and comment out this particular new position assignment and uncomment this one. So to get Flerp to act like Slerp, you send in the start point and the target point. Then the callable, which must always be a function of two floats here, I call them f and n, would return the sine of f times n divided by the sine of n, which would be that sine of omega here. After that, we pass in t, and finally our normalization value, which is just calculated in line here the same way as before. When we do that, Flerp is going to call sine of t, which in this case is 1.0 minus t, times n, and divide it by sine of n, which is what this is doing, and then add it to sine of t times n, again omega, divided by the sine of n, which is the exact equivalent function. So after I do that, even though we're not specifically using Slerp here, we're using the new version, this is what we get. The exact same behavior. So what if we want to dress that up somehow? There are certain constraints you have to put on your function here. It can't be anything arbitrary if you want usable results. As an example, at f equals 0, you've got to be at your first point, and at f equals 1, I'm sorry, t equals 0 and t equals 1. Nope, I did have f here. Okay. You need to be at your target point. So it does have to be a smooth interpolation, unless for some reason that's not what you're going for, but I can't imagine what it would be. And n needs to be the maximum amount that this first part of the function can be. Since f is between 0 and 1, and it's multiplied by n there, you know, in this case it's just going to be that omega. This is something you will have to play with a bit. And you know, you might think that it might be fun to do something with the normalization factor, but usually you just end up with an out of control elevation on your point. So what can we do though? Well, what if we want to control the elevation, but we still want it to come back down in the end? Like with that sine I was talking about, between 0 and pi, it does a full half sphere. So why don't we try something with that? If you look at my new function down here with Flerp, it's very similar to the spherical interpolation, but at the very beginning here we have 1.0 plus 1/2 times the sine of f again. I'm kind of wishing I'd named it t underscore again now, but you know, whatever. F times pi, right? So this is going to go from 0 to 1 back to 0 along the transition. We want 1.0 plus 1/2 of that, so it should go from 1 to 1.5 back to 1. And this is all multiplied by this value, which is what we used to get our original point. Because of that, when I run this, we get this basic missile arc, or airplane arc, from one point in the globe to another. There's a slight skip when you click again, of course, because it's setting P0 to be wherever it currently is, which is much higher. But that's alright, because it restabilizes. The tricky part is getting it to stabilize properly. Whew. You know, I might have to make a game with this myself now. Lastly, just while we're here, let's go ahead and demonstrate the issue live with using your simple conventional linear interpolation, which is right here. It's using the stock one, which is no different from what I'd written before. It's just implemented in binary here. Start point, target point, and t, which is what's being incremented. And as you can see, it's going straight through the planet to get where it's going. Sometimes you can see it a little bit on the surface, but while there are definitely occasions for this, it's not generally what we're going for or what I'm addressing here. I guess that's everything. Thanks for your patience, guys. I hope everybody had a fun time watching this, maybe learned something new, and have a great month.